Hello, good morning. It is always a pleasure to come here and then share some of the latest things, what we are doing. I have been coming here to this event for many years. So, I will try to bring you all the latest things, what we are doing. So, as many of you know, we are in a very exciting phase here. The number one system, the Sunway TIE Lite has been there for the last several top 500 ranking, but I think in the June we will see some new numbers. We are just seeing this Sierra and other machines are being deployed, but the big challenge is to actually go into the Exascale system, and this is where like a lot of things are happening. We will see whether the next year some machine may come from some country or in the next 2 or 3 years. So, while these machines are coming, as we have been hearing in these talks, you will be seeing that there is a very interesting convergence is taking place like HPC, big data and then the deep learning, and each field is trying to push the other field. Okay. So, once you have big data, people need more HPC, then once you do the big data processing, people want deep learning. So, I tell my students that they have jobs for the next 20 years, okay. They do not have to worry about this. So, continuously we will try to innovate and come up with better solutions. But the more important thing, it is not just the dedicated systems. Now, there is an increasing need also to move these kind of things into the cloud. Okay. So whenever we design some solutions, we have to worry about both the sides. So, today's talk, what I will try to focus, I will start with the traditional HPC, and then I will move into some of the deep learning like Caffe and CNTK, and then try to cover some of the cloud for HPC, like how do you take the basic workload like MPI and all into the cloud. And then there is a tomorrow's talk. So, there I will go into more details on the big data. So, there it will be more into the Spark, Hadoop, Memcached, Kafka, Swift. So, those are the kind of the middlewares which are being used for big data and how HPC technology can actually help in those kind of middleware. And there also I will try to focus on some TensorFlow with the gRPC and then the cloud for the big data stack. So, that is how we will cover all these things happening. Now, if we start with the basic like HPC, as many of you know, MPI has been the de facto standard for all the applications, but at the same time we are also seeing an increasing usage for PGAS, which is like partition global address space. So, this is basically physical memory, but we have a logical abstraction on top of this, and on top of that we have hybrid MPI and PGAS. Okay. So, the broad reason is that MPI has been there for many years. People know like how to program using MPI, but these are good for regular applications. If your application has a lot of irregular communication pattern, it is very hard to do that programming in MPI and get the best performance, and this is where the PGAS models come in, so that it can provide some lightweight one-sided communication. And then the community is taking different approaches, like on the language side as well as on the library side. Here we see UPC, Caffe, and then on this side we see OpenSHMEM, UPC+. On top of that, now since both the models are there, people are also trying to explore, can we combine or can we mix and match? For example, if you have like 100,000 lines of code and that is not scaling on a given architecture, let us say it is an MPI code, it does not mean that the code is bad, because the code was written and it was running okay on some systems, but now the architecture has changed, so it may not be running efficiently. So, the question is, if we can identify which parts are not running properly and then can we change those to the PGAS, then we can have a hybrid MPI and PGAS. And then in those kind of a situation, we can actually run it on top of a hybrid MPI PGAS runtime to get the benefits of both the distributed computing model as well as the shared memory computing model. Then the question is, okay, how do we design this stack? So, this is where I will start all the challenges. So, if you see all these programming models, whether it is MPI or PGAS or you take Cuda or even Hadoop or Spark. So, this is where like the programming models come in, but at the bottom layer we have all these technologies are coming, multi-core, many-core architectures, different kind of networking technologies, the SSDs, FPGAs. So, I call this like from a runtime designer's perspective, these are like supply side. So, that means we get a lot of technology with a lot of features, a lot of mechanisms, but somehow we need to take it through and then deliver the performance at this layer. This is where it matters, the applications has to scale and then get the best performance. And of course, those are written on top of some middleware using those programming models, but this is where the communication library or runtime sits in. So that means we need to take all the latest features and mechanisms and try to squeeze it as best as possible and link it through the programming models, so that the application people, when they are writing the applications, they get the performance in a very transparent manner. This is of course a layered approach. Of course, the community also explores a co-design approach, so that you are not like focusing on only one layer, but you are also working across the layers. So in this context, in my group, we have been working in this area now for almost 25 years. And so if you try to outline like a broad challenge, this is like a wish list kind of things, how I want to design this MPI+X runtime layer, you will come up with a lot of laundry list, like we need to have a good scalability for point-to-point communication, good job startup, collectives. How do you balance intra-node and inter-node communication? Because these days the number of cores per node are increasing, so a lot of communication actually happens within the node. And at the same time, a lot of communication goes back and forth across the node, so you need to balance efficient multi-threading, integrated supports for GPGPUs and the FPGAs, quality of service, hybrid programming, virtualization, energy awareness. So all these things one has to think in a holistic manner, okay, to make sure that whatever runtime or you are trying to design, it actually has wide applicability, and then it gets used at many places. Now, while we are trying to add those features, some of the additional things are coming. This is becoming very important, memory footprint of these libraries and the runtime systems. Now, as we know, like the number of cores on parallel systems are increasing, the amount of memory is increasing, but if you do a quick math, the amount of memory per core is decreasing. Okay, you take a look at all the machines over the last decade, that's what is happening. So in that context, if I design you and give you a library where the memory footprint of the library itself is quite high, people will not like it. Okay, because if I have like a 16 gigabytes, or let's say even a half 512 gigabytes of memory per node, and I take 100 gigabytes out of that for my MPI library, then the application folks will not be happy. So while we are trying to design the runtime library, we need to make sure that the memory footprint is also minimum, and at the same time, I give you the best performance. The other thing is happening, I call it like a DLA framework, discover, learn, and adapt. So a lot of these things, it's just like driving in the Bay Area. I'm sure all of you are familiar. I mean, every day you don't take the same street. Depending on the traffic, depending on the accidents, depending on what else is happening, you take the different routes. And same thing is happening when you are trying to design the runtime. You cannot design the runtime in a static manner. Then you may not get the best performance, because different jobs are running. There could be some conflicts. There could be some network contention. So can you make it even adaptive, the runtime? So that's what I call like how quickly when you run a job, you discover the overall network topology. Then how do you learn the impact on performance and scalability? And then might be inside the library, I might have, let's say I want to do a broadcast, I have 10 algorithms. How do I select which algorithm to run at a given point of time for a given job on a given run? If I can do that, then I'll get the best performance. Otherwise, if I just make the design static, then I may not be getting the good performance or scalability. But then, in order to do these things, you also have to have low overhead. Okay, so just like the driving these days, if you put your GPS or your iPhone is telling you very quickly, I mean, if that takes like 10 minutes to discover which way to go, that is not of no use. Okay, so that's how we need to design this next generation library, so that we do all these things with very low overhead, and but at the same time, we give you the performance, scalability, and fault tolerance. So in this context, let me introduce our solutions, keeping this broad vision into account. So this is many of you might be familiar with this MVAPICH project. This project is going 16 years and going very strong. We started this project almost the day one of InfiniBand. And prior to that, we were working with Myrinet, Quadrix, all those prior technologies. So when InfiniBand came, we were the very first one to jump in. And in fact, at the supercomputing 2002, we had the very first open source MPI for InfiniBand. Okay? And since then, after that, we have been having a lot of optimized version, not only the basic version. I'll talk a little bit about those for GPGPUs, virtualization, energy awareness. So currently, it's being used by more than 2,800 organizations in 85 countries, and these are the registered organizations. A lot of people just download and use it. That's perfectly fine with us. And just from our site, currently we have crossed like 445,000. By the end of this year, I think we'll cross 500,000 downloads just from our site, 500,000 downloads. And then, of course, it is integrated with all other software stacks, different vendor stacks. But it's not just the download count matters. We have been in this community for like 18 years. And currently, if you see the number one system in the Sunway Light is actually using our stack. Okay, so we have taken this project from a university project to a really production system, which is running the number one system in the world, now delivering 100 petaflops. And of course, not only that system, we work with a lot of other kind of systems whenever they come up. So this is just like trying to show a release timeline download. If you see, we are in a very upward curve, like in a steady manner with releases. So this is our overall architecture of the software stack. At the very top, not only we take MPI, PGAS, hybrid MPI, PGAS. Below, we take all different technologies, InfiniBand, IOR, Rocky, Omnipath, and also all the different platforms, x86, OpenPower, Xeon 5, ARM, everything else. But the main thing lies in here. Those are our new designs. We keep on like, first we did the research, and because we are in an academia, we have to come up with a better solution. But once we have the solution, in 6 to 9 months, we take those designs and push it into the stack. And in fact, some of the earlier talks I have told, like if in my lab, we have almost 100 plus servers continuously running. Okay, being also in an academic environment, we have continuous like a kind of an industry focus there also. We continuously run, and now we have capability. If we push a new design in 36 hours, we can see that whether that code is stable or not. Okay, so that's the kind of very rigorous QA effort we are trying to put. So in fact, yesterday, middle of the night, if some of you are in a mailing list would have seen, like we made a very new release with a lot of new features. We are trying to converge on this, the 2.3 series. It has a lot of features. I'll try to show you some numbers later on. Now, so just to give you a little bit of perspective, how we are trying to achieve this scalability and performance. So I'll touch on some of these things. I'll start with some basic communication, startups. Of course, there are a lot of collectives. New things are happening with Mellanox ARP, also CMA-based, XVMA-based. And gradually, we are introducing the dynamic and adaptive characteristics. I mentioned earlier, like a DLA kind of things. So we are gradually bringing very intelligent solutions inside the stack. And also now, in addition to the solution, we are also focusing on some performance engineering with MPI support, integrated network and analysis and monitoring, and I'll touch a little bit of this. So these are the numbers which shows actually over the years, like if you take a different adapters, how the MPI latency is improving. Few years back it was here, and very recently with EDR, you will see like we have 0.98. Okay, so this is like a half of round trip. I send you a message and you send it back. So steadily we are going down into below 1 microsecond. And this is for the large messages. Of course, the network has higher bandwidth. You get better performance. And this one is the bandwidth, like a unidirectional bandwidth, the rate at which I can push the data. And clearly you can see like this is a QDR, FDR, and all these are EDR 100 gigabits. So these are around 12.5 gigabytes per second. If you multiply by 8, it's 100 gigabits per second at the MPI layer we can get. And then the right hand side is the bidirectional. So we get very close to 200 gigabits per second. The other thing is not just the basic performance matter. So this is where I want to bring the holistic nature. Okay, so any runtime stack, you need to look at each and every component. It's just like building a car. If you want like a really sports car, your engine has to be good, your wheels have to be good, your inside designs have to be good. So that's how we try to do. When we do the runtime, it's not just focus on only one part. We focus on everything. So in fact, as the systems are becoming or deployed in a very large manner, the job startup performance itself is becoming a big issue. Okay? I mean, think of like a 10 million course. I just launched an MPI job, 10 million course. If that takes 2 hours, I mean, how can you make it practical? And that's what is happening many times. I mean, you see these jobs. Sometimes this taken in like on the TAC Stampede 2. This is the Texas Advanced Computing Center. This is a 3,584 KNL nodes, so almost 300,000 processes. And this is where you will see this was like an Intel MPI when it was done last year. and this is our solution. So here you can see that we are able to do like a 22 seconds, we are able to start the job on the large scale system, whereas some other libraries like Intel MPI was just failing kind of thing after 64K. Of course, now they have improved looking at some of our solutions. So that itself also becomes a very big challenge. So you need to make sure that anytime these new technologies, and what we have done is not only we have this solution, in fact, we have a lot of patches for Slurm. Many people use Slurm with MPI. So we have actually made those available. So if you are running Slurm, you take our solutions there with those patches and you run the MPI library and you will see this kind of performance. And the right hand side is also like this is on the oak forest packs in Japan. You can see like we can do an MPI init on 64,000 processes in just 5.8 seconds. Okay, by the time you sip a cup of coffee, it's already the job has started running. So then that is like a startup. I showed the point-to-point communication. Now let's come to collective communication. This is becoming a big challenge. Collective communications like broadcast, all-to-all, reduce, all reduce. Those who are familiar in the community will know that performance of these collectives have a lot of impact on the overall performance. Okay, it's like the Amdahl's law. This is where all the systems need to synchronize, and if you cannot accelerate it properly, you don't get the benefits. So here, like a first level solutions, we are trying to do like a Mellanox SARP. I think in some of the talks you might have heard of. So they are trying to do a network based offloading. So we have actually integrated that into our stack. So you can get actually in an application level benefits like 12 to 13%. This is like those are like a small messages. So in fact, as I'll be talking a little bit more, you will see that gradually there is a lot of focus coming to optimize medium and large messages. And these are actually coming from deep learning workloads. Okay. Many years back, like MPI designers used to say only optimize the short messages. Okay. But now the deep learning workloads are trying to exchange a big amount of messages. So we also need to focus on the medium and the large scale. So here we have introduced a new solution which was presented at SC17. We call a multi-leader approach. And there you will see that using this kind of solutions, we can, this is like a 10,000 processes, we can give you like even a 32K message all reduced, we can improve it by a factor of 2.4. Okay. And these solutions are already available. Like we have the MVAPICH2-X version. If you want to utilize these solutions, you can use that. So then this is the newer kind of solution we are trying to introduce. This is called CMA based or a kernel based solutions. Many of you might be knowing when we started the MVAPICH project, we had a module called kernel module called LIMIC. Okay. So in order to handle large data transfer, instead of doing 2 copies, we can do 1 copy. And then gradually that concept has been adopted by the Linux stack, and that is known as CMA, cross memory attach. A lot of other stacks use those things, but you will get benefit. But if you do collectives using those calls, you will see there is a lot of contention happens within the kernel. And this is what we are trying to alleviate. We had a contention-free algorithm with CMA. This got the best paper finalist at the IEEE Cluster Conference last year. So here if you see as you have different kinds of nodes, sometimes we can give you a factor of 7 benefits, factor of 4, factor of 2 kind of benefit. In all these multi-core systems, you will get a big factor of improvement if you utilize these kind of schemes. Again, it was a paper, but it is again, we have pushed the solution into the MVAPICH2-X, and then you should be able to see the benefits. The other kind of things is a very fresh result. We just had a paper accepted for IPDPS 2018. So this is called the shared address space or XPMEM. Some of you might be knowing this is a module which is being developed in Sandia National Lab. So this is a shared address space. So using that kind of a solution, we are able to actually achieve 0 copy reduction. Okay. Through an effective XPMEM based solution, we are able to provide very good performance. Again, here you can see for very small messages to large messages, we can give you like a factor of 2 or factor of 4x improvement. We are trying to incorporate this into our next release. And using this kind of solutions, you will see that this is a deep learning workload like a CNTK AlexNet at an application level 20%, 9%, or even 27% kind of benefits we can give. Because these are the collectives which try to slow you down. And then if you can have a runtime with very optimized implementation of these collectives, you will see you will gain benefits at the applications. Now coming to the dynamic, that DLA kind of a property, many of you might be knowing in an MPI stack, some of you might have known like there is a threshold below which we say like it is a eager, above that we call it a rendezvous. Different libraries have that threshold which can be tuned. Okay? But most of the time again these tunings are done statically. Okay? So, that means either the library uses it or as an user you can change it, but per run that is what you can do. Okay? So, here there is an example. Let us say you are like some processes are communicating like that, like 0 to 4 wants 12 kilobytes of threshold, 1 to 5 wants 64, 2 to 6 wants 128, 3 to 7 can have 32. Like the threshold is not same for all pairs of processes, then obviously you cannot do it on a static manner. So, the question is, as the job started running, can you detect this? And then can I adjust it in an appropriate manner? And then if I can make it dynamic and adaptive, this is where I will get the best benefit, good overlap, optimal memory requirement, high performance, high productivity. And that is what like here we are trying to show the solution, like this is an execution of the Amber. Not only you get good performance, your memory consumption is very minimum. That is what I said, like using this kind of solution, you can try to reduce the memory footprint, trying to give you the best performance. So, in fact, this paper got the best paper award at the ISC 2017, that is the Hans Moore Award, and we are trying to incorporate this into our solution. So, it will be available very soon. Similar kind of things we are trying to also work on tag matching. Those people are familiar with MPI, you will see like many times you get a lot of unexpected messages, and you need to internally you need to handle with the tag matching, and there you require again a lot of buffers, and the performance depends on how you do the tag matching. So, this was a best paper nominee for cluster 2016, and we have again a dynamic and adaptive tag matching scheme. So, this is like the green line, you will see that you will get the best performance and see the memory footprint, very small compared to the other kind of solution. So, once again we are trying to bring that solution into our stack. So, then more importantly, like these are the solutions happening inside, but then the question is how people can, let us say you are an end user of an MPI application and you run the job and you are not seeing the performance. So, how we can help you? Okay. So, this is where like in fact the MPI forum has come up with a solution. I do not know how many of you know there is something called a MPI-T interface. How many of you have heard of this MPI-T? Okay. So, this is like a MPI tools interface, MPI forum introduced in the standard 3.1. So, the idea is that earlier what can happen is that the MPI library used to be like a black box. You just run and you do not know where the time is being spent. Okay. Now, this is trying to make the MPI library as a white box. So, we can actually instrument it, and then exactly when you run it, you can say that, oh, my time is being spent in this call, or this buffer is taking more memory. The more kind of information you can provide, it can give you to the tools, and not only that, you can do the analysis and you can drive the library in your second run or subsequent run, or in fact sometimes even the same run, let us say it is running, the application is running for 30 days or even 7 days or even 2 days. After 4 hours you can do the analysis and then change all these thresholds for the second phase. Okay. So, I call it like a personalized MPI. Okay. In fact, many of you must have heard of personalized medicine, a lot of people are working on. This will lead us to a path where for your job on a given machine, it will be able to automatically tune it. Okay. So, that is the kind of goals we are trying to achieve, and currently we are working together with Tao from the University of Oregon team. In fact, this got the best paper award at the Euro MPI last year, and we already have this kind of a support in our MVAPICH2 and Tao. If you use them properly, you will be able to get a lot of this kind of white box approach. So, then on top of that, we also have trying to provide you a integrated network analysis and monitoring. Of course, in the field, I mean, there are a lot of tools where you can see the different kinds of behavior, like the network topology, where the traffics are going. There are a lot of tools, but what is not there is like the integration with the application. Okay. So, this is what we have provided. So, in fact, let us say a job is running, you can actually drill down the job. From the jobs, you can exactly find out on each link how the traffic is being distributed. Okay. Because InfiniBand had a lot of monitoring facilities, and we have used that kind of a facilities through the GUI tools. So, you can say that, okay, how your collectives are being used, or what link got choked during your collectives. And it also has this tool has historical information. So, it is not just that while it is running, you can keep it into a like store it and then revisit it, and then say, okay, why my run on yesterday during this time gave me terrible performance. Okay. And was it an algorithm issues, or it was a machine issue, or it's a combination issue, and then you can try to resolve it and then come up with a better algorithm and then run it next time, and you will see get better performance. So, those are the kind of like a broad overview of the different kinds of things what we are trying to enable the community, so that you get better performance, scalability, and also engineering. And then let me move into this hybrid MPI and PGAS kind of things I indicated earlier. So, this has been there like since last 7 years we have been working on this, which is a unified communication. So, I call it like a diversity. As many of you know, like in a typical team, you might have several members, everybody does not have the same strength. But as a manager, you can actually try to see that how to take everybody's expertise together in a complementary manner to give you the best performance. And that is what we have done here. If you have like a different programming models for a given program, how do you write each part using properly? Some parts can be MPI, some part can be OpenSHMEM, some part can be UPC++. So, everything can run actually on this system. Okay. And so that for an end user, it gives you the complete flexibility. You do not have to stick to one programming model. You can mix and match and then try to see what works out the best. Here there are two concrete examples. We did this was a Graph 500. We looked at the basic Graph 500 MPI algorithm, which does not scale, and this was actually a work by a PhD student for like 9 months. Okay. So, we are able to find out where things are not scaling, and we modified some of those parts with OpenSHMEM, which is the PGAS model. Then we stitched them together. So, it was a hybrid program, and it was able to run on our unified library and see the benefits. This was on TAC, the previous Stampede one. On 16,000 core, we are able to improve by a factor of 13. Okay. It is not just like a few percentage, factor of 13 we are able to improve just by working on for one student for 7 to 9 months. So, think of these like especially on the labs, there are like all these codes which are there for many years, and people are not getting the performance. One can actually utilize these kind of techniques to get benefits on the modern systems. So, similarly, like these are like some of the PGAS things as the modern machines are coming, like a KNL kind of architecture. If you see, it has AVX, MCD, RAM. We are trying to take advantage of those mechanisms to provide optimizations in this case for OpenSHMEM. So, next let me touch a little bit about GPUs. So, this is a field where we are working very closely with NVIDIA for the last several years. So, in fact, in 2010, we introduced actually from my group this term called CUDA-aware. How many of you have heard of this CUDA-aware MPI? Some of you, that is good. So, in fact, this was the ISC 10 paper we introduced. The idea was that most of the time if you see like this is a CUDA or a GPU cluster, you basically take the data from GPU using a CUDA call, then you do an MPI, then do another CUDA. So, we asked the question that if you do like this, you may not get the best productivity. You may get the performance, sometimes performance may not be good, or sometimes the productivity is not good. So, what we asked the question that if you are an end user just knows how to use MPI programming from host memory to host memory, can he or she just use the same construct from CUDA buffers. So, in fact, the person does not need to know CUDA at all. Okay. So, you just do MPI send from a device buffer, MPI receive from receive buffer, and everything else happens within the MPI. Okay. And that is what you see the animation. So, the data gets moved from sender to the receiver within the MPI library, and within the MPI library we know all the different characteristics, and we can do proper pipelining, we can do proper copying, we can handle the buffering, so that the end user does not have to know at all. So, this is the CUDA-aware concepts we introduced, which can lead to high performance and high productivity. And after that, we have been trying to work very closely with NVIDIA over the last several years, trying to take advantage of all the features, whatever gets offered with NVIDIA and then CUDA, and trying to integrate that into our stack. Now, if you take a look at all the latest our version, see this number, I want to really stress this. This is like a 1.88 microsecond. I can move data from one GPU over InfiniBand to the other GPU, 1.88. And what did I show earlier, like the InfiniBand basic host memory, it was like 0.98 microsecond on the EDR. So, we are able to give like within another 1 microsecond, we are able to give this kind of a performance. Of course, this utilizes like GPUDirect RDMA. There are some libraries like GDR copy. David is sitting here from NVIDIA, so thanks for his contribution. So we are using all these latest things from NVIDIA, put them together, so that as an end user, you can actually get this kind of performance benefit. And that helps significantly, like this is a Humdi Blue application. Now, you can see that you can get at an application level significant benefit. This is a very classic case studies. In fact, if you have visited Switzerland in the last 2-3 years, or if you will be visiting them in the future, you will see next time you are in Switzerland, you open up your iPhone, see the weather that is being driven by our MVAPICH2-GDR stack. Okay? So, we have a 3-way collaboration happening between Switzerland Supercomputing Center, the Meteo Suisse, who is the meteorological organization in the Switzerland, and us, and we are able to give them the real best bare metal performance from the InfiniBand and the GPUs. So, that is why they are able to run very accurate weather forecasting there. Now, also in the GPU field, there is a newer kind of applications are coming. These are called streaming applications. Okay? So, think of like sensors are there. The sensors are sending the data. A lot of surveillance is happening. So, those are the data are coming, and you need to operate on them. Okay? Of course, people are using GPUs, but the challenge is how do I push the data to the GPUs? Okay? So, unless I take the data to the GPUs, then the operations cannot happen, and this has to get overlapped. Okay? So, that means the applications themselves might be also using PCI resources as network, and we want to have minimal interference. Okay? So, this is a project we just finished, collaboration with Department of Defense, and using that we actually combined GPUDirect RDMA from the NVIDIA, and then the InfiniBand hardware multicast from Mellanox. So, these were the 2 latest technologies from 2 different organizations, and put them together into an MPI stack. And then if you see, the data actually comes directly from the source, it goes through the switch, and then typically in most of the solutions, people first take the data to the CPU and then copy it to the GPU. Okay? But here we can totally avoid that. So, we do not need a PCI Express or anything, directly data goes to the CPU, goes to the GPU, and then concurrent processing can happen. So, then those are like some of the initial solutions. We are continuously working on the newer kinds of system, OpenPower and ARM. So, we have actually enabled this from last several months. So, this is the very first OpenPower host kind of a performance, and this is the ARM. Here you can see like within the node between 2 cores, we can give you like a almost 740 nanoseconds kind of things. And this is actually on the NVLink and Pascal. So, I think Adam indicated the Sierra kind of system. So, this is exactly these systems with NVLink. So, at an MPI level, you see intranode bandwidth, we can actually give you 33.9 gigabytes per second, which is coming very close to the peak NVLink bandwidth. Okay? And these are all available in the latest MVAPICH2 version. If you have similar kind of systems, please feel free to download and use this. Now, while we are trying to do that, we are also keeping a look at not just at the low level, we are also looking at the applications. So, here these are some very latest runs which has happened on the TAC Stampede 2. If some of you are familiar, at the Stampede 2, they have a KNL platform, they also have a Skylake platform. So, these are some of the like MiniFP, Neuron, Cloverleaf, these are some applications you can see you get very good performance with respect to scalability with our stack. These are some of the very latest like the release which we made recently. We have done a lot of optimization, that is what I indicated for KNL, Skylake, even OpenPower, all the platforms. So, here you can see like this is the spec MPI 2007 on a KNL plus Omnipath. We are able to even deliver better than Intel MPI. This is like a commercial product, but we are able to give in fact better performance than that. This is the Skylake. For some application, you see up to 38% benefit we are able to give compared to Intel MPI. So, we are able to optimize a lot of these on the communication stack at the lower layer. And while we are going through these kind of exercises, in fact, we have created a best practice page on our MVAPICH site. So, if you go there, this is the site, and we have a lot of contribution from the community. So, the idea is that, as many of you know, any MPI stack has library has 200, 300 parameters to tune. And that too, the architectures are becoming so different. So we really want a lot of feedback from the community. If you are working with some application, we can work with you. And if you would like to contribute your results with the credits to you, we can just link it so that the other people can get benefited. So that's the kind of a community involvement we are trying to achieve. So with that, let me just very quickly look at a little bit two other aspects, deep learning and then the virtualization. And as we are hearing, what are the challenges in the deep learning? So the deep learning, as I said, currently what is happening is like the unusually large message sizes are happening. That is a very big difference. Like in a typical MPI scientific applications, people used to say, okay, optimize 8 bytes of all reduce, 16 bytes of all reduce. Now the deep learning is saying it still remains 816, but it's not bytes, it is gigabytes, megabytes. Okay, so you need to totally rethink how these new algorithms need to be designed, and that actually provides the scale up and scale out. So what we are trying to do, in addition to focusing on the scale up and scale out, we are also proposing a lot of co-designing. Okay, so not just the lower layer, but also working with the upper layers. So this was like earlier we did our MVAPICH2-GDR with a nickel 1, and then a tight integration. So there you can see like with a CNTK, we can give you like a 25% benefit. This was a Euro MPI 2016 best paper. Recently we have actually published one. This is, you will see like we are trying to compare in the community. Some people feel that nickel based solution is good, Baidu all reduce is good, MPI based. So we are trying to actually provide a solution. Here you will see that if you do properly, your MPI solution is good enough for all these kind of scenarios. And we have optimized all our MPI collectives since like a GDR 2.2 GA, because these are the kind of operations which typically deep learning people use. Okay, so if we can optimize these collectives, your deep learning workloads will benefit. And here recently we compared with Baidu all reduce. Some of you might have known, those who are working in the deep learning field, they just introduced saying, yeah, just use Baidu all reduce, you will get very good performance. But that is not true. If you compare with our MVAPICH2-GDR all reduce, for different message sizes, like a medium message sizes, we can give you 10x better. Small message sizes, almost 100x better. Even the large message sizes, 20% better kind of things. So then in the co-designing, we have also gone up a little bit, like this is a Caffe. Many of you might have heard of this. So here we have optimized, done a co-design, so that not only the lower layer is optimized, also the Caffe layer is optimized. So this is actually available. We call it an Osu Cafe. Here you can see we can scale up to like 128 GPUs easily. So then let me just round it up by saying these are the solutions on physical cluster, but then how do we take this into the cloud? Okay. So when we are talking about the cloud, of course, the best performance, people also want the performance. See, that is the challenge. Nobody wants a LPC cloud, I call it, like a low performance cloud nobody wants. Everybody wants high performance. Okay. So the broad idea is that virtualization has the benefit, but how we do the runtime design so that we don't lose performance. Okay. And that's what we have done. In fact, InfiniBand has some support like SR IOV. We have done some very tight integration, and we have the support OpenStack, Docker, Singularity kind of things. And here you will see some of the solutions. Just at a higher level, I want to explain this kind of a graph, which is the basic MPI can do. The right-hand side is the gray, which is the bare hardware without virtualization can do. Okay? So, and that gap used to be like, here you can see depending on different application, you will see 20-25% as people were losing. So this is the orange line which we have introduced earlier. That is our solution. We have a very optimized MVAPICH2 library. So where you can actually come to the bare metal performance with 1%, 2% degradation kind of thing. And that's what we call like a HPC Cloud. We have a Docker solution. We also have a Singularity solution. And the next thing we are actually focusing, which is the real hard thing, which is the migration. Okay? Because we also want like the jobs not just to run. Virtualization has the latest, greatest benefit of virtualization, how we can do it over InfiniBand. Okay? So this is the solution we have. It has not been pushed. This design was proposed, presented in the IPDPS 2017. So here you can see within the lab we did like this. Virtual machines were running. This is a very simple latency bandwidth test, but we were able to migrate the VMs from one node to the other node, and then it again got migrated. So that's why during the migration time, the time was high, but then it again came back. It re-established connections and everything, and then continued. So those are the kind of solutions we want to push. So with this, let me conclude here. What I indicated, like in the motivation, that the next generation software stacks, when you are trying to design HPC systems, you also need to have a holistic view of the deep learning and cloud, because those are the kind of things what is coming up. And I presented some of the solutions, and tomorrow I'll talk a little bit more on the big data and the associated deep learning and HPC. So with this, let me just thank all our sponsors, but more importantly, these are all my heroes who do all the hard work. What I'm presenting here is like a work of like 18 years. People, students who have built on top of each other. So I just come give a talk, but they continuously do the hard work. So I just want to give credit to them. With this, let me stop here. If there are any quick question, and if there is time, we can answer it now. Otherwise, I'll be here until tomorrow, and then we'll be happy to answer. Okay. Any quick questions? Yes, please.
What's the relationship at OSU between work on MVAPICH2 and the libfabric and OFR?
Yeah. So that is a good question. So as some of you know, so the question is, okay, what is the relationship between MVAPICH2 and then the libfabric? So the relationship, in the sense, these are all our work based on verbs. Okay, so that's what we've been continuing. And those of you who are familiar, like there is an alternative stack which is coming called libfabrics. So we are gradually moving into that, but so far it's not public yet. So these are all internal things. So we are not also seeing, just like anybody else, like whether libfabrics will succeed or not. That I'm not sure. So that's why we just don't jump into anything just like that. So
we could have a conversation offline.
Sure, definitely. Thank you. Any other quick questions? So if not, thank you.